Okay. Another form of determining the age of fossils is radiometric dating. I want us to realize we have two parts in this word here, radiometric. The word radiometric. We have radio, I can cut in two syllables, or two parts, radio, which comes from the word radioactive. I'll explain that. And I have the word or the part metric, which simply refers to measurement. Metric means measurement. So we have radio and we have metric. Now, radioactivity. Radioactive comes from the word radioactivity. It is used to describe substances that give off nuclear radiation. Okay, like radioactive elements. Radioactive elements are elements whose atoms are not very stable because they have too much energy. They're holding up too much energy. So sometimes they want to give off packets of energy in the form of photons, so that when they lose energy, it's like they're kind of calming down so that they can become more stable. And when they do so, they also break up, they disintegrate. These atoms disintegrate in a way we call decay, just like they are decaying. So nuclear radiation is useful because when nuclear radiation occurs, causes radioactive substances to decay, and this decay is not at random. It's happening at a fixed rate. That's what makes nuclear radiation very important in estimating the age of fossils or the age of anything, because we all have radioactive elements. Any living thing has radioactive elements and is also found in non-living things. So we have this radioactivity occurring all the time around and in us. But what we are saying is that it occurs at a fixed rate, and it's important because it can then be calculated. We can then use it to estimate the age of something because we know exactly the pattern, the rate at which it occurs. We know that, for example, after 5 years, the radioactive element must have decayed, or the atom must have decayed to this much. After another 5 years, must have decayed to this much, and so on and so on and so on, so that we can easily calculate how much time has passed. If we meet a current quantity, we can compare it to what it should have been as an original quantity. The current quantity will be, for example, of lower mass compared to the original quantity, which will be of a higher mass. If we see by the difference of masses, then we can estimate how much time has passed from big mass to small mass. Then we can use it to estimate. So we can then use this knowledge to find the age of fossils. We are going to see exactly how. Like I said earlier, we all have radioactive elements, living and non-living organisms. But living organisms are made up of organic molecules, and you will remember that one major element that is found in every organic molecule is carbon. And living organisms have two forms of carbon. We have carbon-12 and carbon-14. Carbon-14 is radioactive. It means that it is unstable and would always want to disintegrate and give off packets of energy, and the mass will keep on reducing. But when it reduces, it forms something new. When an organism dies, the carbon-14 will start disintegrating and converting itself from being carbon to becoming nitrogen-14. And then carbon-14, in the process of changing to nitrogen-14, it changes so in a very fixed rate. It means after a certain time, an amount of carbon-14 would have been converted to an amount of nitrogen-14, so that we always have different amounts of nitrogen. As carbon-14 is decreasing, nitrogen is increasing. So we have fixed amounts of the two elements at every given time. So it means that originally there should be, say, 100% carbon-14 compared to 0% carbon-14. Or 100 carbon-14, let me take it as one example, and 0 carbon-14. At a certain time, some amount, let's say 10 carbon-14, would have to convert to 10 nitrogen-14. It means we'll be left with 90 carbon-14 versus 10 nitrogen-14. If another 10 again convert, then I'll be left with 80 carbon, 20 nitrogen. Another 10 again, then I'll be left with 70 carbon and 30 nitrogen. So it converts itself at a fixed rate so that we can now develop a ratio. If I have 70 versus 30, then my ratio is 7 carbon is to 3 nitrogen. So scientists can then work out the age of the fossil by comparing the ratio, by comparing how much carbon-14 is left compared to how much nitrogen-14 is being made. So by establishing that ratio and knowing how much time it takes for a particular amount of carbon-14 to have successfully converted into nitrogen-14, then I can always work out how much time must have been spent. And that will give us the time, the age of that fossil. Okay, now that we have looked at both methods of determining the age of the fossil, it's good to know that both methods can actually be used to determine the age of the fossil. For example, if we have a case where we had a volcanic eruption at a particular period and era, then because the organic molecules that make up the body parts of all organisms contain carbon-14, it means we can use radiometric dating to determine the age of a fossil that will then form during that period. And we can also use the time. If we work out the time when the volcanic eruption occurred, then we can use relative dating to estimate this time. We are estimating the age of the fossil by comparing the fossils with the date of the eruption relatively. Hence, if the fossil is found somewhere in the layer above the volcanic ash, it means that the volcanic eruption has occurred, everything has cooled down, the ash has dropped back on the ground, and a fossil now comes and forms on top of that ash. It tells us that this organism died after the eruption and fossilized after the eruption. By then knowing when the eruption occurred, we can work out an estimate of the age of a fossil that formed after that eruption. Similarly, if the fossil is formed at the layer below the ash, it means that that fossil formed before the eruption, and when the eruption came over, it then covered the fossil with ash. That's what we could do to determine the age of the fossil by both methods.